You're in the water loop.
Waterloop. Inside infrastructure, there's a simple device called a check valve, quietly protecting water systems from chaos, stopping dirty water from flowing backward, and keeping everything running smoothly amid bigger storms, tighter regulations, and growing cities. In this episode, Cal Hayes from Proco Products explains the vital role of check valves. Before starting the episode, I want to share more about the sponsor. Waterloop. I'm endlessly fascinated by how water infrastructure works. I admit I never knew much about valves before this conversation, but it's eye-opening to learn the critical role they play. I learned so much from Cal at Proco Products, the leading manufacturer of rubber check valves. These fully passive devices require no maintenance, no outside power, or manual assistance to operate. Proco's check valves are ultra quiet, won't warp or freeze, and are designed to prevent standing water while eliminating trapped solids. They're perfect for water and wastewater, pulp and paper, mining, and stormwater applications like outfalls. Proco Products offers options to fit every scenario, like the Series 700 ProFlex rubber duckbill check valves, a cost-effective solution for controlling back pressures in sewage and tidal operations. Or the ProFlex 710TT, engineered for 100% mixing in potable water and sewage systems, ensuring less downtime and lower costs. For powerful performance, the ProFlex 730 coarse bubble diffuser delivers bubbles strong enough to carry sewage effluent to the surface. Please connect with Cal and the team at procoproducts.com. Waterloop. Cal, I am very excited to have you on for this conversation to go deeper into the world of infrastructure. People are generally familiar with some of the bigger pieces, right? Pipes and pumps, but we know that there's so much more to these facilities and to water management, the hidden side of infrastructure, if you will. Wanted to talk to you today about valves, about check valves. Could you explain for parts of the audience that aren't as familiar with these, just what is a check valve and what is the role of one in a water system?
There's lots of different valves. There's valves in your home. There's valves in your toilet. That's basically a check valve. You flush the toilet. You don't get smells back up. That's a kind of a rudimentary type check valve. Spinning into the industrial world or the water world where Proco kind of lives, there is check valves that are designed to stop sewage from coming back up into municipalities, into the parking lots of buildings, into infrastructure. These check valves can spin from the typical old style steel check valve, stainless steel check valve, flap gates, which are considered to be a check valve. And then you spin into our world, which has been around since the early 80s, and that's called the rubber duckbill check valve. So in that case, we have a large medley of check valves depending on what the application is.
So you go, if you look at a drinking water facility, a wastewater facility, an industrial water facility, you're going to find a variety of check valves used in a variety of ways. It's just basically key to keep things flowing in one direction and not back, right?
Right. Exactly right. Yeah. So, let's go clean water first. So
yeah.
We get up in the morning, we go and brush our teeth, we go and grab a glass of water. We all rely on our municipality or our tax dollars to ensure that we're going to get clean drinking water and it hasn't been infiltrated with sewage overnight or caustic chemicals or something like that. Spinning into the dirty water side, sewage side, we also want to make sure that the costly ventures of treating sewage to make sure sewage is now broken down into a small, minute particle and not, sewage number one after it flushes through the toilet is also guaranteed that that treated sewage is not going to be allowed to come back up into a tank or a reservoir that's already spent a lot of money on chemicals to make sure that sewage breaks down.
So a failure with one of these valves or problem there could be a public health risk ultimately. There's a risk to your process, whatever your treatment process is. You can contaminate that and lose time, lose money, lose chemicals,
Right.
all those kind of pieces. It's a valve we're talking about, but look at how it's critical to the whole entire process.
It is.
Yeah.
Yes, most definitely. And again, I mean, going back to an engineer designs a system, whether it's drinking water, whether it's sewage, whether or not it's just simple rainwater running down the street and it's running down into a storm drain. Nobody wants that water to come back up. You have seen, I have seen, all of our audience has seen streets that are flooded by water. And that water.
You mentioned these different types of valves and the evolution of the material even. Could you talk a little bit more about that? I'm always fascinated by like the way infrastructure and even parts evolve.
Right. We're now just going to talk about elastomeric check valves, rubber check valves. Where did it come from? Why do people like that idea? First of all, it won't rust. First of all, it won't torsionally twist because of waves out into the ocean because it is flexible. So when the waves hit it, it's allowed to flex, it's allowed to move, it's allowed to twist. If it's in a river current and the river's pushing this way, it's allowed to push, but the bill or the lip of the valve remains in a shut position.
Wow. Yeah, so it's that flexibility to a lot of different conditions and situations that those can be in. When did that material and that style really kind of rise to popularity?
So rubber's been around a long time. The evolution of rubber is the fact that we can now cure rubber and it becomes one homogeneous piece of rubber. And the way we do that is through vulcanization or autoclave. So it goes into an oven, similar to you cooking a cake in the oven. All the media, all the different types of products get wrapped into this part, and it becomes one homogeneous piece of rubber designed for specific applications. Let's say I'm going to drop this valve into a potable water tank that's filled with chlorine. In the other side, we can have a elastomeric check valve that's going into Saudi Arabia, for instance, and it's going to be sitting in 130 degrees temperature all year round. So now we need to make sure that the rubber is also designed for that. We also have rubber that can be put down into the bottom of the Atlantic Ocean, the Pacific Ocean, that we don't want barnacles and algae to start growing on the outside of the valve like you see on old relic type ships. You see massive amounts of barnacles. We want to make sure that that doesn't happen as well.
Wow, that is incredible. Just all those different environments that rubber can adjust to and be durable and withstand. Because again, like you talked about metal rusting, you want something that's going to last for a good amount of time. Shifting gears a little bit, you kind of alluded to some of this. There's a lot of pressure on water systems and water infrastructure. We've got more extreme storms. We've got these high tides. We've got growing cities. We've got regulations even. There's all these kind of pressures. How do valves fit into that? How are they evolving, if you will? Is it even more critical that they are so durable and adaptable? And what types of situations, like I've mentioned, are they more important for? I just gave you like 3 questions in one, Cal. You can figure out where to go with that.
I mean, the reassurances are, and I think a lot of the engineers around the global planet working on sewage and wastewater, and, they can sit around at a board meeting on a Monday morning and say, gee, how are we going to fix this? We've got a problem. I'll just give you a quick spin. We had the U.S. military down in Djibouti in Africa that had a problem with valves. And so, fortunately they came to us, and, the questions with the engineering firms were, how are we going to fix this application? And so we, as Proco, our engineering department, the world and wonderful, wacky way of building valves, come up with a design for them that has been spectacular, works extremely well. And the thing about that part of the world is they have huge, what we call rogue wave. So rogue wave is that wave that you hear about on the news that flipped a ship over last night and that type of thing. So those waves, when a valve is sitting like this facing the waves, and the waves comes rolling in and hits this valve, and let's say the valve is in a full open position and
Yeah.
allowing water to flow through it, it also has to make sure when the wave hits it that the valve doesn't get turned inside out, and then it becomes a failed valve.
What other kind of, are some of the emerging challenging situations or the certain cases that you have to kind of craft things for?
We always need to be really reassured that our water is good and that we're drinking proper water. And so, in the last couple of years, we've really, really done some study on that. We've worked with some big universities to do studies on valves. I mean, we've got some valves that are really neat. I mean, I showed you the typical elastomeric type check valve a moment ago, made out of rubber, and it's the elastomeric. And now we're coming into valves that look like this. I mean, this is a patented valve that Proco and myself have worked on. As you can see, this valve has a spinning or torsional twist to it compared to a standard rubber check valve. And in this case, these valves are being used in potable water tanks. So you're driving down the highway, you see this big dome in the middle of the highway where you live, I-79 or a place like that, and it says, "Welcome to North Carolina," or something like that on it. This is what's in that tank. So inside of every single water tank across North America, we, not just Proco, but engineering firms, municipalities have to guarantee to you that the inside of that tank is completely being mixed. And by mixing, I mean like you taking a blender in the kitchen again, we're mixing something up. We have to make sure that those tanks are mixed, particularly in areas where you get hot days, very hot days, and then cold evenings. So what's happening in that tank, if it's not being mixed, you're getting what's called cold spots or hot spots in the tank, which then becomes stagnant water. And stagnant water now can create germs and disease. So, and again, going back to this valve is designed for blend or twist. So when the water is flowing through this valve off of the pump that you mentioned a moment ago, which is the bigger part of our whole discussion today, that pump is pumping water into the tank. When the water is going into the tank, it's now being pushed or forced to come through this valve into the tank, and it's coming out in a mixing motion, very similar to you watching a propeller on the back of your outboard motor on your boat. You see the spin, and what the spin is doing is creating agitation or cavitation in the water, which is creating a perfect blend of the water, so we're not getting hot spots, cold spots.
Wow. So that's incredible that, again, designed for a specific situation, it actually is capable of dealing with that mixing and contributing to the mixing with its own flexibility, both. I think you might have a couple other ones dealing with some of these new challenges, right? Flooding is a big deal. Like I mentioned, the intense rainfall, especially along the mid-Atlantic, right? We've had it here in North Carolina, but you've dealt with situations in like New Jersey, right? With flooding and coastal risks and everything.
I mean, like you said, coastal risk is becoming more and more of a problem. And some of the big issues that we've come about is traditionally there would have been a flap gate hanging on the end of a pipe. And as you know, and as I know, there's more and more people that want to go down and spend the day at the beach. So they don't necessarily want to see a big old steel flap gate creaking and racking back and forth in the waves, or when the flow of water comes out from the city or what have you. So for a long time, a duckbill check valve like this would be put on the end of the pipe. And that became a valve that people would say, you know what, that looks okay. It's not so bad, but what do you got that's better than that? So, and it's a thing where you don't want a car that looks all rusty. You want a car that looks all nice and shiny. Same
Sure.
Kind of
Is this at the end of like an outfall pipe?
Yes,
where there's a discharge, right?
You'd always see it on the end of an outfall. So what happened then was people came along and said, hey, I'm laying on the beach. I don't want to see a big old valve hanging on the end of a pipe. or on the end of an outfall and you see water flowing out of it. And even if it's not a rainy season, you're still going to have a certain amount of water dripping out of the pipe. So along comes the new type of valve, which is
Mm.
inline. It's going inside the pipe. So it's kind of like out of sight, out of mind. Wave actions love it. The wave goes into the pipe. The cup of the cone of the valve stops the wave action from going back up the pipe and coming back up onto a street or flooding or that type of thing. It's become the real valve of the future. They won't have any barnacles growing on it, which is one of the biggest thing we always get with engineers saying, we cannot have barnacles. Barnacles will, barnacles, they grow very, very quickly and they will stop the valve from closing properly.
So this is a case of not even an environmental pressure or something like that, engineering issue. It's like aesthetics, just the looks that, you've got to adapt to that too.
Yeah. Yeah.
I mentioned regulations a couple times. I think you had an example maybe from out in Oregon around, regulatory compliance forcing you to adapt also.
So that project was, again, how are we going to build a valve that's going to guarantee that the outfall portion of the valve, this is an area that they wanted regulatory wise that they had to ensure that whatever was going to be attached to the manifold of the pipes were going to guarantee that they weren't going to have smudging or areas of the pond or the river front that was going to be disturbed by sewage or treated sewage. So we designed a valve, it's quite common, but instead of the valve being, let's say, 3 inches here, port size is also 3 inches here. In order to get a broader spectrum of diffusion, we built a valve that had very, very wide lips on it. So what that meant was that these valves are sitting in a vertical up position. The sewage is flowing into the valve. This is treated sewage. But again, going back to regulations, they had to make sure that it was being diffused or the diffusion was proper across the bottom of the channel that it was going to be put into. So regulations are very important. It's very, very important that we follow those regulations and that we're, let's say, one step above it so that we know exactly what we need to do to make sure that, first of all, we're honoring the engineer's request, but we're also ensuring to the municipality that our valves are going to be properly placed, properly located, and properly manufactured to give the right flow conditions. We also have a valve that has become a real answer. And this is more on the industrial side.
Okay.
This is a lot of people will have valves, check valves, in a pumping situation that is introduced to large back pressure. So let's say the pump shuts off and the pump is down here and it's 100 feet to where that pump is pumping sewage up and allow it to flow out into a tank or a reservoir or what have you. When the pump shuts off, they get what's called valve slam or water hammer. And it comes back and just a loud bang, and it can tear pipes apart. This particular picture here, these are 30-inch diameter valves. Prior to us putting those valves in, they had a typical swing gate, like a double door check valve in there. And it was hitting so hard that it actually broke the check valve off of the concrete wall. And so then they come to us, and the neat thing again is that it's not that our steel bodied valve is anything different than anybody else. It's the fact that it has a rubber check valve inside of it. So the neat thing about rubber, again, like we talked about a moment ago, is that the rubber is flexible. So when you've got back pressure, water slam that would normally slam a steel gate shut, with this sitting like this, energy, which we call energy, we have to dissipate the energy very rapidly. And that's what stops valve slam. So when the water is coming back, it hits the side of the valve because it's rubber, it's allowed to flex. And that immediately takes the inertia or the energy away to stop valve slam or water hammer.
This is a world you've been in and done some incredible innovation in. What do you see next? And you're always
Well,
adapting to certain situations, right? And just kind of almost case by case in a way. Technology's changing so rapidly. That includes materials and designs and all this stuff. What do you have any insight on kind of the future of these valves that are so critical in water infrastructure?
I think the world is asking for things to be made faster and faster and with less chance of failure. With us as a company, Proco being what we consider to be on the forefront of design, of listening to people like yourself to say, hey, I've got a new headache and how can we fix that headache? And in that case, then we go back to our recipe book, if you want to call it that, and we can say, hey, look, we built the valve like this. We built another valve similar to this. What can we do to make it differently? So
Mm,
again, going back to what I mentioned a moment ago, these valves here, this pretty white one is made out of urethane. All right. So
yeah.
it's a rubber. Okay. But it's not the typical put it in the autoclave, wait the 4 hours, wait the 5 hours, take it out, do the trimming. So these are urethane. So with urethane valves, which is on the forefront, these valves are poured. So, it's like mixing up a bucket of water. You pour it into a mold and you get this. So again, the rapidity is fast. Once the mold is made to build this type of valve, and we can build valves at a much, let's say, I don't want to call it faster, but we can make a valve faster to supply to the customer and with a different design. Urethane. Urethane is very, very flexible. It flexes forever. It doesn't have a wear pattern like the old type of elastomer does. It doesn't have any fatigue. Let's call it that. It doesn't have any fatigue memory, which
Yeah.
is phenomenal.
Well, I think a little bit about the unseen part of infrastructure, and unseen things are underappreciated, right?
Oh yeah.
Maybe the bigger, maybe certain people in the utility space or whatever don't appreciate these valves. But from talking to you today, it sounds like the engineers and the people that actually work inside these facilities and systems all the time probably have a deep appreciation for these valves and the ways that they work. Would you say that's fair?
Oh, very fair. 100% fair. I mean, we're one of the hidden things, right? Our world of check valves is amazing. I mean, Proco is on the forefront for listening to people, and I think that's the biggest thing for us in the water and the dirty water side. I mean, we're global.
Mm,
You cannot imagine the different types of questions or queries we get for different applications, and I'm talking like, okay, we've got different types of a world. We've got areas that flood drastically overnight. So now our valves also have to be designed to handle huge chunks of trees and branches and, mudslides and that kind of thing flowing down a channel and then eventually gets to our check valve that has to be able to open up, allow the flow of water through or dirty water, trees,
mm,
trunks, that kind of thing,
uh,
and then be able to still operate at the end of the day. So,
Again, I'm a self-professed water nerd and was not versed in valves. And I appreciate this conversation. I feel so much more educated, not an expert, but I'm aware now of this hidden part of being inside infrastructure. Cal, thank you so much.
well, thank you. And thank you for inviting me to do this.
You're in the water loop.